Testing on YouTube. Testing on YouTube. Testing on YouTube. Testing on YouTube. Tsetse fly. Tsetse fly. Tsetse fly. All right. Working on YouTube. Perfect. How's it going, Sarah? Spit up this gum. Take a sip of water. All right. Let's close out the YouTube and we'll wait for X. How's it going, Zheyu Zhang? Oh, there we go. Live on X. Let's double check. Make sure the audio works. Make sure it's all working. Broadcast is not available, of course. Come on. Come on. Come on, X.com. Testing, testing, testing. Testing? Maybe? All right, yep. We're working across all of our platforms. Let's go ahead back to this so I can see the YouTube chat. And let's go. All right, welcome everybody to another Hoopo stream. We're going to be going to the world of robotics and reinforcement learning today. We're going to be looking at a paper from DeepMind. The name of the stream is called Egocentric Vision RL. It's in reinforcement learning using egocentric vision. And specifically, it's this paper here. This is Learning Robot Soccer from Egocentric Vision with Deep Reinforcement Learning, right? So reinforcement learning, deep reinforcement learning means you're doing it with deep neural networks to approximate things like the policy and the critic. Vision is cameras. Egocentric vision is a camera that is attached to an embodiment, right? So in this case, it's attached to one of these little robots, and it's kind of from the point of view of the robot. Released 3 May 2024. This is only just the latest paper, right? This is a research group within Google that basically continuously releases these papers. We've reviewed some of their papers before, but this one is going to be particularly interesting because they're finally using vision. A lot of the previous papers, they were always using kind of explicit state, and now we're finally seeing a vision version of this, and I think they actually mention it as well, but this is, to the best of our knowledge, the first demonstration of real-world transfer for vision-based policies trained with end-to-end RL for a dynamic long-horizon tasks, right? So dynamic long-horizon tasks just refers to the fact that soccer or football, whatever you want to call it, is dynamic. There's a lot of stuff happening, stuff moving around. You have different agents. It's also long horizon, which means that the length of a specific episode, the length of time that a game or like a little one-on-one scenario takes is quite long, right? And then reinforcement learning is very sensitive to the length of time, the duration of that episode, right? It makes reward stuff a little bit more complicated. And then real-world transfer, that refers to the fact that this is going to be trained entirely in simulation and then zero-shot deployed into the real world. Right, sim to real has historically been an issue for reinforcement learning. So real world transferring, specifically a vision-based policy, that's quite impressive, right? Real world transferring a policy that uses states, right? That's a little bit easier, but vision-based, quite hard. So we're going to get into it. How's it going? Brian, Zenji, Boo, and Khalil. And Ikel Fonxion. How's it going, guys? All right. So right off the bat, one thing that I thought was a little bit weird is that when I saw all these names here, right, you got pretty much everybody here is working for DeepMind, 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 but then there was these names right here that are not DeepMind, and I was like, what the hell? Who are these guys, right? And usually the way that names are organized in a paper, this is going to be your senior people, right? So the back end, the last names are the most senior people, and then the beginning names are usually the junior engineers that are doing most of the work, right? So most of the work was done by this guy here, Dhruva, but Dhruva and Marcus are probably quite junior, right? I would guess these people are probably either directly outside or directly out of a undergrad or PhD program. So they're relatively young versus these people here, Martin Reed Miller, Nicholas Heese. These guys are going to be more senior. So I was like, who are these people here that are not associated with Google at all? And I looked them up, and they're lab techs. So Marlon Guira is a lab engineering maintenance technician. Neil Srindra is a lab engineering maintenance technician. So these are basically the lab techs who sit around in this environment and kind of probably clean the robots, fix the robots, set up the playing field, kind of adjust all the cameras, like do all the kind of like low level dirty work that you need for any kind of real robotics application. And I actually, when I worked at Google, there was a similar type of situation when I would work there, right? Where you would have these little lab techs, and the unfortunate reality of capitalism is that these lab techs are not actually employees of Google. Usually the way it works is these lab techs are vendors or temps. They're called TVCs, temp vendor contractors. And it's a little creepy. I'll be honest with you guys. The dichotomy that you have in these industry labs, where you have basically the full-time employees who come from prestigious universities and are getting paid hundreds of thousands of dollars, potentially even millions of dollars, to work on these advanced things. You see how they all have the Google DeepMind. And then you have this like almost like lower caste of people who aren't full-time employees and who are temps, vendors, and contractors, and who are just there to basically clean up after you, right? And the creepy part about it is that they can be fired at any point, right? They're a TVC. They can just get fired left and right, versus these people here, they're never going to get fired unless they do something seriously wrong. So there's this weird, like, creepy vibe where they're basically just trying not to get fired, and they're always trying to be helpful and always trying to be there and make sure that they're on the best side of everybody. And I don't know, I just find it really creepy. Like, if these guys are contributing enough to put their name on their paper, like, give them a full-time job, you know? Like, don't have this weird, like, underling, like, lower class of people that are just there as contractors and can be fired at any moment and live in this constant fear of being fired, right? If you respect them enough to put their names on the paper, give them a fucking full-time job. I was not in DeepMind. I worked at Google Brain in Mountain View, but I got to work with some DeepMind people, and they're quite intense and quite cool. All right. Okay. So let's get started with the abstract. Now that I've officially caused some issues, in case some DeepMind people are listening, and now they're thinking I'm an enemy of the state because I called them out on their hiring practices, let's get into the abstract. James McLean, isn't academia explicitly supposed to recreate feudalism? Tenure is supposed to approximate a landed lord of some kind. Yeah, there's a similar kind of vibe in academia too, right? Where like the advisor kind of like owns the PhD people, because the kind of graduate students, they need the advisor to eventually give them that piece of paper, right? And it's even worse than that, because a lot of graduate students a lot of times they're international, so their ability to stay in that country is based on their employment as a graduate student. So if the PhD advisor tells you, hey, you need to do this, you got to listen to him, because if you don't listen to him and he ends up not liking you, that might be it, and you might get fired. And once you get fired, then you have to leave the country, because you're really only able to be there because you're a graduate student at this university. So yeah, academia and then DeepMind, because everybody comes from academia, also kind of has a similar vibe, but that type of shit just always rubbed me the wrong way. Yeah, serfhood with extra steps. It's not great. But all right, let's keep going here. We apply multi-agent deep reinforcement learning to train end-to-end robot soccer policies with fully onboard computation and sensing via egocentric RGB vision. So even though this group is in London, right, they should call it football, right, because British people are European and you call it football, but they're the ones that are calling it soccer. So even though I'm going to be calling it soccer this whole time, I'm American, so I say soccer, they're also calling it soccer. So don't get angry at me for that. Okay, so multi-agent. The reason this is multi-agent is because you have multiple robots, but it's kind of a stretch, you know, because it's multi-agent in just a 1v1 sense. You know, to me, if you're going to be using that word multi-agent, like, it's got to be more than two, you know, like 2 is like barely multi-agent. So a little bit overstated there. Training end-to-end robot soccer policies. End-to-end refers to the fact that the policy or the neural network that is actually going to be performing actions in the world is going end-to-end. It's going straight from, in this case, egocentric vision, which is going to be image, all the way to an actual joint command, right? So like it's actually controlling all of the different joints of this robot. You can see there's 20 different joints on this robot. You got your head, you got your shoulders, hips, knees, blah, 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 all the way down. I don't think there's a toes, but maybe there could be. And the policy is controlling end to end. It's taking in the raw signal and then outputting the raw control signal. Okay, so that's the end to end part of it. And another impressive thing here is that this is going to be using fully onboard computation, right? And sometimes for a big enough robot, fully onboard computation is not that impressive, because if a robot is big enough, you can basically just put like a big NVIDIA GPU inside of it, and that's not that impressive, right? So like a fully onboard computation for like an autonomous tractor, not particularly impressive, right? Because the tractor's so big, it's got a huge ass battery, you can put a big ass computer in there. But these little tiny robots, these are small boys, you know, they're very tiny. So the compute on this is something along the lines of like a Raspberry Pi or a Jetson Orin, like very tiny little packages. So doing everything on board a tiny robot like this, that's quite impressive. And they have a trick for doing that involving distillation, which we're going to go into. So this paper is really great in terms of it's a good implementation of all the different hard parts of reinforcement learning in a real-world system, right? This setting reflects many challenges of real-world robotics, including active perception, agile full-body control, long-horizon planning, and a dynamic, partially observable multi-agent domain. So it's tackling all the hard problems at the same time, and it works. We rely on large-scale simulation-based data generation to obtain complex behaviors from egocentric vision, which can be successfully transferred to physical robots using low-cost sensors. Low-cost sensors here just literally being the camera and an IMU and the joint encoders. To achieve adequate visual realism, our simulation combines rigid body physics with learned realistic rendering via multiple neural radiance fields. So they're going to be using a nerf to render the background of the simulation, right? Because they're going to have to train this entirely in simulation and then deploy it in the real world, zero shot. So whenever you do that, your simulation needs to be very accurate, or at least has enough domain randomization that it kind of adapts to the real world. And that's usually very difficult to do. But in this case, they combine kind of classic simulation, which is, you could think of it kind of like a video game, right? So you have rigid body physics, which means you have a little sphere, which is a mesh, right, with a texture on it, and it's bouncing around on a plane, which is also a mesh with a texture on it, and you have the goals, which are also meshes and textures. But then the kind of background is going to be a nerf, which is a cool little trick. You know, I don't think it might not even be original. I think there's probably other robotics papers that have a nerf as the background, but I thought it was kind of cool, so props to them for including that. We combine teacher-based multi-agent RL. This teacher-based is going to come down to this distillation idea that we're going to go into once they get to that. Cross-experiment data reuse to enable the discovery of sophisticated soccer strategy. This is cross-experiment data reuse is going to refer to one of the techniques that they use, which comes from one of these guys. So Dhruva Tirumala, right, has also done previous work at DeepMind, and one of the previous works that he did was, I don't actually know if that's a guy or a girl, and I'm sorry if I got that wrong. I don't know if Dhruva's a guy or a girl, but replay across experiments, a natural extension of off-policy RL. This is going to be kind of the earlier work, which is, we'll get into it, but that's where the, this part here, cross-experiment data reuse. Okay, we analyze active perception behaviors, including object tracking and ball seeking, that emerge when simply optimizing perception-agnostic soccer play, right? Emergent behaviors, everybody's favorite thing to read about in these reinforcement learning is whenever you get emergent behaviors, because that's kind of like the coolest part. The agents display equivalent levels of performance and agility as policies with access to privileged ground truth state. So they're going to be comparing to using explicit state, and we're going to get into what that is, but explicit state is pretty much what everybody uses, and it's way easier to do than vision, which is partially observable, much harder, much more higher dimensional. To our knowledge, this paper constitutes a first demonstration of end-to-end training for a multi-agent robot soccer, mapping raw pixel observations to joint-level actions that can be deployed in the real world. It's going to be a good one, guys. All right, so let's start here. So here we have the environment. So these little robots are inside this little 4x5 meter pen soccer field with these little rubber squares. And the rubber squares are important because these robots are not particularly agile, you know, even though they say they're agile, they fall over all the time, and they kind of, you see, look at that, look at them go. I also just love how adorable these are because they're very small and tiny, but they fall over all the time, so you got to put them inside this playpen that is basically just covered in rubber so that they never really damage each other. They also have these little bumpers on them, so the front of the robot and the back of the robot, they have these little rubber bumpers so that whenever they fall, they don't break down, right? A lot of the humanoid robots have that problem. We saw in the DARPA robotics challenge, right, which is quite dated at this point, but the DARPA humanoid challenge, right, there was famous compilations that people made where it was basically all the humanoids just falling. And these humanoids, if they fall, like especially in something like this, right, imagine this type of humanoid, which is like an early version of Atlas, like falling down on a bunch of concrete bricks. It's gonna get fucked up, you know, like it's gonna break. You're gonna get a hydraulic hose that pops and then bleeds everywhere. So if they fall constantly, it doesn't really matter. Okay. We train agents purely in simulation and align the simulated environment with a real-world environment to enable zero-shot transfer. So zero-shot transfer there, they're going to be basically taking the policy that is learned in simulation and applying it in the real world. They're not going to be collecting any data in the real world. In simulation, the camera view consists of a NeRF rendering of a static scene. So if we actually zoom in here, let's zoom in. Enhance. All right, here you go. So you see how the simulated camera, you have some of the classic kind of simulated stuff here, like the ball and the robot and the goal. So the ball and the robot and the goal are all being represented as a mesh with a texture on it, which is one type of 3D representation that you use in simulators. But the background here is a NeRF. A NeRF is a neural radiance field. It's a more modern type of representation for 3D environments, and it's a good way of capturing just a generic kind of background. NeRFs allow you to render a view from any kind of arbitrary viewpoint, so they basically NeRF the entire inside of this room, right? And then they use that as the background and then kind of superimpose these more dynamic elements like the robot and the goal. One thing I realized is that whenever you talk a lot, I don't breathe out of my nose, I breathe out of my mouth, or I breathe into my mouth and out of my mouth, which means that my nose starts running. And I've kind of become hyper aware of this, and like I've started looking at, whenever I listen to podcasts, I start to think about, okay, is that person nose breathing when they talk or mouth breathing when they talk? And I think I mouth breathe when I talk, but I think that's actually not optimal. I think if you look at people who are good at podcasting, they nose breathe when they talk. So, I don't know. I'm working on it, guys. In simulation, the camera view consists of nerve rendering. In the real-world environment, which is 5 meters by 4 meters, we use the output of a head-mounted RGB camera. Agents receive a downsampled 40 by 30 resolution image. So this is a very tiny image, right? Even though this is reinforcement learning being done entirely through vision, which is impressive. One of the problems with doing vision-based reinforcement learning is that the input space is very high, right? Even a 40 by 30 images of 40 by 30 pixels, that's still way more than like 100 different joint states and positions and rotations and stuff like that, right? So explicit state is still way lower dimensional than vision, even if you're using a very, very tiny camera. But it still shows you that we're super early days, right? Because at some point, we're going to want to do end-to-end RL with images that are way higher resolution, like 4K images, a stereo with 4K images, multiple cameras, right? But we're still very far away from that, especially if we want to be running things on board, right? On these actual tiny robots, they just don't have the compute required to consume a big image every single frame. So you have to aggressively downsample it in order to even run it at a reasonable control speed. Okay. Blah, blah, blah. These results are promising. Notably, many of these examples rely on depth sensing or external state estimation. Okay, so I've talked about this external state estimation. What am I really talking about here? And in order to make my case, I'm going to bring up RoboCup. Okay, so RoboCup is a competition that I actually got to attend one of these. So there, at one point, I was in Japan, and they had a RoboCup, and I was there for it, and it was pretty awesome, not gonna lie. You had like a bunch of these fields, and there's a bunch of different leagues. So this is like the mini humanoid league, but they have like a larger humanoid league. And then they also have, I think the most famous one is this one here, which is called the RoboCup Small Size League. And these are extremely impressive, right? These little robots, which are these little mobile bases that have those omni wheels so they can kind of move around everywhere really quickly, they're extremely fast, right? And these guys are doing 11 versus 11 or 6 versus 6 matches. And these robots move so quickly, and they do these very coordinated attacks and very interesting kind of set pieces. This is way more advanced in terms of like the social multi-agent aspect than what they're doing here in these 1v1 soccer games, right? But this is DeepMind, right? So this is like the cream of the crop reinforcement learning people. Like, how are they getting beat on the complexity of the task by kind of like your average, like almost like high school level robotics competitions? The reason is that in RoboCup, you're using explicit state, right? So what does that mean? That means that in this thing, there's a camera that's at the top and multiple sets of cameras, and they're staring down, right? And you see how these robots have these little stickers on them? Those little stickers are being used to track the robots. And every single team, so both teams that are participating in this 11 versus 11 small size league game have access to the position of every single one of these robots and the position of the ball, right? So if you go here into the RoboCup resources and rules, right? So here's the 2024 rules. We can click on the 2024 rules, and then in the 2024 rules, you see blah, blah, blah. They have all this stuff, but you have this shared software, right? So what is that? What do they mean by that? And you can actually go here into the RoboCup GitHub. This is a proto, which is a type of message, right? So you can basically think that there's a computer that is kind of like the referee computer that has access to all the cameras. And that referee computer that has access to all the cameras is sending a message to both of the teams simultaneously. And that message, which is being sent to both of the teams simultaneously, contains the entire explicit state of the whole board, right? So it has the team of every robot. It has the position of the ball. It has the velocity of the ball. It has whether or not the ball is visible. It has the position of every single robot. It has the orientation of every single robot. It has the velocity of every single robot. It has the angular velocity of every single robot. So that's what we mean whenever we're talking about external state estimation, right? You're estimating the state of the game, which is where all the little robots are, where the ball is, the velocity of the ball, the velocity of the robot, and that's being done externally, right? It's not being done from the robots. It's not like the robots are calculating where all their friends and their opponents are. That's being given to them explicitly by basically the game master in this game, right? Which is the referee, which has the Oracle kind of cameras that are tracking, right? And doing reinforcement learning or any kind of agent using explicit state information like that is significantly easier than doing it from images. And that's why you can look at this DeepMind Soccer and you're like, I don't understand why people are hyping this, because it seems like you're doing 1v1 soccer. Like, that seems way easier than like this shit here, where you have like multiple like 6v6 soccer, and they're using humanoids too, right? But the key difference there is that this is end-to-end RL and that this is using vision rather than external state. And that's why this is impressive, is that they're able to do this with just vision. The league sounds pretty awesome. Never knew there's a league for robots. Yeah, I mean, you should definitely get involved. It's pretty popular. Like, whenever I went there, and this is probably 2017, 2016, something like that, is the one that I saw in Japan. But there was a lot of teams, and it was like super international. It's not like professional. Like, the dudes that compete here, they're not like grown humans, you know what I'm saying? It's very clearly some kind of like, it's like a high school kind of like college type of situation. So it's like different colleges of different teams, but it's very impressive. Like, the speed at which these move, and like they have these very coordinated attacks. It's like, it's very cool. If you're into that kind of stuff, like the first robotics challenge, like Robo Soccer, I would definitely recommend. Pixel to action. Yeah, basically end to end is pixel to action in this case. Okay. In this work, we present an RL pipeline for training vision-based policies. Our policies use purely onboard sensing, which is also difficult to do, right? They could have done this very easily with the compute running in a server, and then it just streams it to the robot, but they actually run the robot, the models on the actual robot itself. And in terms of the proprioceptive and kind of inside-out information that the robots have, they really only have an IMU, joint encoders, and a head-mounted RGB camera. Okay, so joint encoders are basically going to give you this information here, right? They're going to give you the position of each of these joints, which is just going to be a number, right? So you just have some number which tells you where your knee is, right? It's telling you where within the min and the max value of your knee is, right? And then you have your head-mounted RGB camera, which is just a very cheap kind of webcam running at 30 frames per second. And then you have an IMU. So most of you probably already know what an IMU is, but an IMU is an inertial measurement unit, and this is basically just like a very, very tiny little chip, right? Your phone has one of these as well. And an IMU is composed of usually a couple different chips, sometimes redundant chips, so there'll be a couple of these in there, but you have things like a magnetometer, an accelerometer, and a gyroscope. And what that gives you is an accelerometer, for example, will give you the acceleration along 3 axes. A gyroscope will give you the rotation speed around 3 axes, and a magnetometer will give you kind of like a magnetic kind of alignment, right? They're popular since they're inexpensive, small, and power efficient, and can be embedded inside any object to enable intelligence. These things are not perfect, though, right? So these IMUs, you can't necessarily rely on them entirely to give you a perfect 6-dimensional or 7-dimensional, if you're using a quaternion, estimate of the position of the robot, right? So even though you have this IMU, you don't actually know 100% what the position of this robot is compared to this external state estimation, right? The velocity and position estimate and orientation estimate that you can get from an external camera tracking system is significantly more accurate and precise and fast than the position and orientation estimate that you can get from an IMU. Okay. Egocentric vision renders the environment partially observed. So partially observed here is referring to the fact that this is a reinforcement learning is usually has this Markov decision process as the base assumption. In this case, it's a partially observable Markov decision process because you don't have the real state space, right? So the real state space would be something like this, right? The position and velocity and orientation of every single robot and the ball and everything, right? So the explicit state of the entire system. But you only have a camera which is partially observing some of that, right? It only has a guess of that. It's only looking at a subset of the information that describes the whole state. So that's why this is a partially observable system. Amplifying challenges of credit assignment and exploration. Credit assignment is the problem that in reinforcement learning, you have a reward, right? Which is usually coming from, in this case, if you score, you get a reward of 1. If you don't score, you get a reward of 0. But when you score and you get a reward of 1, which of the state and actions that you were in over the course of this very long horizon task were actually good and which were bad, right? Like which of the tiny little micro movements were useful and need to be assigned credit versus which of the tiny micro movements were bad and you should not assign reward credit for that, right? So this credit assignment problem is quite difficult to do, especially if you have a long horizon task, and especially if you have a long horizon task that is partially observable. Okay. Requiring the use of memory and this discovery of suitable information-seeking strategies in order to self-localize, find the ball, avoid the opponent, and score into the correct goal. And the cool part is that these are going to be emergent, and that's going to be the pretty cool stuff there. Okay. They're going to be using MuJoCo as the simulator. MuJoCo is one of many different robotic simulators that are popular. There's a billion of these, right? You got Isaac Sim, which is NVIDIA's. You got PyBullet, which used to be the open source one. But MuJoCo has gotten a little bit more popular because DeepMind decided to open source it. So MuJoCo used to be paid. Like you used to have to get a license, and then you had to basically pay for this license, and you could only use it if you were doing this license, if you had this license. But now that they've open sourced it, everybody has moved from the kind of previous open source simulators into MuJoCo. So MuJoCo is kind of having a resurgence where, because it's now open source, everybody's kind of using it. But I don't know. It's still, there's still so much movement and activity in the robotic space now that I don't know if MuJoCo is going to end up being the simulator that everybody uses. It's just kind of for historical reasons. It's the one that Google uses, and the fact that they open sourced it means that it's a little bit more popular now. But you know, NVIDIA has a ton of money, so maybe Isaac is going to be the one, and game engines are also very popular for this, like Unity, Unreal Engine. So the simulator battle has yet to be determined. Okay, no explicit rewards for active perception. Information-seeking behaviors such as searching for the ball emerge naturally. Okay, so what they're talking about here is that a lot of times when you're training these reinforcement learning systems, right, you have this difficulty of credit assignment and exploration. Exploration is, you want, whenever you're training this thing in simulation, you want your policies to explore parts of the state and action space that are not, that you don't have experience for, right? So you want your robot to kind of have some incentive to explore maybe kicking it with the left foot as opposed to the right foot, or like maybe moving in this part of the kicking it from over here rather than kicking it from over here, right? So there's this difficult exploration problem. And a lot of times, the way that people solve this is that they do reward shaping, right? So they basically manually design these very complicated reward functions that give you some reward for finding a novel state, or give you some reward for finding the ball, right? So like the closer you are to the ball, the more reward you get, right? If you score a goal, you get reward. If you score a goal from far away, you get less reward. Like, so usually there's this kind of very complicated reward shaping process which people do in order to get these reinforcement learning systems to work. But actually, in that kind of vein of thinking, another thing that we've seen is we've now seen large language models being used to design these reward functions, right? So one kind of view of RL is that we will discover reinforcement learning algorithms that are so good that you can give them a very simple sparse reward, like just 1 for scoring and 0 for not scoring, and that'll be good enough. Another kind of branch of research is kind of what the research group at NVIDIA with Jim Fan and the Eureka and Dr. Eureka papers are, which is, okay, well, what if we still do reward shaping, but rather than doing it manually ourselves as humans, we get a large language model to write the code for the reward that shapes and ends up being used to train this policy and the critic and all of that. So two different paths there. I tend to be along the path of the no reward shaping. I think that we're going to figure out reinforcement learning algorithms that don't require extremely manicured and shaped rewards, as opposed to kind of the LLMs will write the rewards for us. But the jury's still out. We don't know which one of those two methods is going to work better. Question from Arkagioti. Are this realizable in constrained resource device? Yeah, so I mean, this is being run on board, right? So the policy for this is being run at, I think, 40 hertz on the actual robot computer. And that's why this is very small, right? So if you look at this policy here, it's called the actor. The actor and the policy is the same thing. It's a very small residual network, which is consuming this image. You have a small little LSTM here. You have a little multi-layer perceptron, also quite small. So the reason these are very small is because it literally needs to run on the robot. So a resource-constrained edge device such as the robot, you're not going to be able to run a 70 billion Llama 3 at 40 hertz on that, right? So you're going to have this little tiny little model that's doing all this stuff for you. Okay. Blah, 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 blah. At the end of the introduction, they summarize their key contributions. Emergent vision-specific skills, including active perception, and vision-based RL agents maintain a similar level of agility to state-of-the-art agents with access to ground truth state information. All right, and that's really the main success story of this paper, is that they're capable of getting pretty good results with just vision, which is much harder than this ground truth or explicit state. Okay. We're going to get back to this when they describe the reinforcement learning a little bit later. Blah, blah, blah. Rather than distilling policies using state-based agents. Okay. There's going to be a two-stage reinforcement learning pipeline here. The maximum a posteriori policy optimization is the specific type of reinforcement learning algorithm they're using there, right? There's a lot of these. You got PPO. You got like 20 different versions of these, but at the end of the day, they're kind of the same thing, right? You have a policy, which is your neural net, and you have your critic, which is kind of like a value function. It's telling you how useful certain states are, certain state actions are, and then your policy is actually picking the action given certain state. Okay, so you're going to have two stages here. The first stage, two separate experts are trained, one that learns to get up from the ground, and another that learns to score a goal against a fixed random opponent. Okay, so you actually have two policies. Right? You have one policy that the only thing it knows how to do is get up from the ground. So once the robot's in the ground, it knows how to get up from the ground. And then you have a second policy that actually knows how to score a goal. And it's not even like, I think this one is okay. So it's not just like a penalty shot. It's like the one that actually moves and scores, right? And it's separate from the policy that gets up. So if you have two separate policies like that, one thing you could do, which is what some people do in robotics, is they have kind of a hierarchical structure where they have a higher level policy that picks lower level policies to play in specific scenarios, right? So if it notices that it's on the ground, the high level policy will say, okay, let me play the low level get up policy. And then once that's done, then I'll play the score a goal policy, right? So you have this kind of hierarchical, kind of high level policies, low level policies. But that's not what they did here. What they did here is a little bit more interesting, and what they do here is they distill these experts into a single agent using KL regularization, right? So what does that mean? I have here, is it this? This? That's KL. This is what I want. Okay. So distillation, that word distillation, what does that mean, right? So in distillation, you have a teacher model and you have a student model. Your teacher model is generally much bigger than your student model, right? And what you really want to do is you want to take this teacher model, which is big and it knows a bunch of things and it has a bunch of knowledge, and you want to distill that knowledge into a little model. Because maybe what you really want to do is run a model on the phone, and this big teacher model, it doesn't work on the phone, right? It's too big for the phone. So you've tried quantizing it, you've tried pruning it, making it sparse, it doesn't quite fit on the phone. Okay, well now let's just train a little small model which can fit on this phone, and we'll train it to basically mimic the teacher. So what you do is you take your training data, this has already been trained, and then you feed that training data to the teacher, and you feed the same training data to the student. The teacher will produce some output, and the student will produce some output. And then you can say, okay, I want the output of the student to match the output of the teacher. So I'm going to have a loss function that basically takes the difference between those and pushes that gradient into the student, right? And then if you do that over and over and over and over and over again, right, you're just sampling batches from your training data, feeding it to the teacher, getting the output, and then using that to basically supervise, learn the student model. Eventually, you will get a little student model that is not quite as good as the teacher model, but pretty close. And that little student model is now significantly smaller and can be run on a mobile phone. Pretty good, right? So what is one of the ways that you can do this type of knowledge distillation? So here they mention KL regularization. KL regularization, stands for Kullback-Leibler or something like that. It's basically a metric. A metric means it's something that gives you the distance between two things. So here you have two distributions. You have a blue distribution and you have a green distribution, right? So one of the weird properties of KL divergence is that it is not symmetric, right? So the KL divergence between P and Q, between the blue and the green, is different than between the green and the blue, right? And this is some random Twitter dude who just posted a nice little GIF that kind of demonstrates that we're here, right? Whenever the two distributions are right on top of each other like this, the KL divergence is small. Whenever the two distributions are not similar at all, the KL divergence is either big or small. I think I flipped that, but it's basically a distance metric that you're using to try to make the student model be as similar as possible to the teacher model, right? And there's another interesting dimension to this, right? Where, as I described distillation there, that was mostly for the purpose of making it small, right? So I described distillation in the sense that, okay, you can use this to make a smaller version that you can then run on a mobile device. But you can also use distillation to combine multiple models, right? So in this case, they have two different quote-unquote teachers or experts, right? One of them just gets up from the ground and another one learns to score. Okay, so the same way that you can use distillation to distill a big model into a small model, you can use distillation to distill two different teacher models into one student model, right? So you can imagine having two teacher models here, right? One of them is the ground model and one of them is the shooting model. And then you're alternating batches of training data into this and then basically pushing gradients into this little student model, some of which are coming from this get up model, some of which are coming from the teacher model. And you'll end up getting a model that kind of isn't quite as good at getting up as the original get up teacher model, isn't quite as good at scoring as the original scoring teacher model, but is a kind of a combination of both of those, and it's a single model. And that's important, right? Because if you want to do everything on board, right? If you want to do everything on the actual robot, on this tiny little edge device that is the robot computer, you can't do hierarchical reinforcement learning, right? You can't have a higher level model that is picking lower level models to run, right? Because that would mean you need to run the higher level model and then you need to be able to run the lower level model. And that's a whole lot of models that you don't have the GPU memory to run on this tiny ass little robot. So distilling multiple teacher models into one tiny little student that runs on the robot and takes up the full compute and memory that is available on that robot, that's a very powerful idea, and I like it much more than the hierarchical kind of approach that you see sometimes. Question from Pratyush. Why can't they score a goal without getting off the ground, or is this to avoid a penalty for playing with hands? The reason they need the get-up model is because these little robots fall over constantly, right? So if you were... So you see that? See here how that little robot just almost immediately falls over? Look at this. So they start on the ground. Boom, it gets up. You see it try to, oh, and then boom, it falls over again, right? So they're constantly falling over, so you need to have the ability to get up, right? Versus something like here, there's no get up model for these robots because these robots don't fall down. You know, they're literally statically stable at all times. They don't really ever, maybe they do. Maybe they move so quickly that I'm sure they kind of flip over sometimes. But you need to be able to get up with these little robot humanoids because they're just constantly falling down. Question from Zhang. Is the teacher fixed or EMA? So EMA is exponential moving average. That refers to sometimes when you're doing these kind of distillation setups, you have more than just one teacher in one model. You might have multiple teachers and then your teacher is the average of those teachers, or you might have multiple students and the average and the final student is the average of those students. So EMA is usually a kind of like a regularization, which you're using to basically prevent one particular set of weights from dominating over a different particular set of weights. Usually the average of a couple different sets of weights is more stable and better than any one individual set of weights, especially if you're kind of feeding batches of data from the GetUp model and the teacher and the shooting model kind of like alternating. So there probably is some kind of EMA fancy shit going on here, but they don't mention it in the paper. Okay. All right, let's keep going here. So we talked about KL regularization, we talked about distillation, and now we want to talk about LSTMs. And this is great because yesterday we were literally just talking about LSTM. So we had a stream on the new LSTM, which is called XLSTM. But here, they're going to be using just a classic LSTM with a long unroll length to incorporate memory over time. Okay, so what do we mean by a long unroll length? All right, so if we go to an LSTM is a type of recurrent model, right? And what that means is that it's recurrent. The output of one state depends on the previous state, depends on the previous state, depends on the previous state, right? So there's what an LSTM is doing is it's basically accumulating information over time, right? So it's looking back in time. So here you have x of t, and then an x of t minus 1, x of t minus 2, x of t minus 3, right? So how far back you're looking at in time is kind of a hyperparameter that you have to pick, right? So is your LSTM just looking at the past 5 states, or is it looking at the past 20 states, or is it looking at the past 100 states? The longer you look back in time, the more information you can get, right? Especially for something like this, where if you only look back one state, so if you're only looking at your current state and then you're looking at your previous state, you might not even see the ball, right? So you might not be able to guess where the ball is if you only have access to the 2 previous frames. So a long unroll length here means that the LSTM has access to a long previous time horizon, which allows it to pass a hidden state forward through that LSTM that contains the information such as, hey, I saw the ball 10 steps ago, but I still kind of have an idea of where the ball is because my LSTM has taken that information that the ball was over here 10 steps ago and recurrently passed it forward to now where I don't see the ball anymore, but through this hidden state that is being passed forward in this LSTM, I kind of have an idea of where the ball is, right? And I think the 64 here refers to the fact that it's 64 steps in the past. So the amount of previous steps that is going into this LSTM is 64. And then they mention that this is running at 40 hertz. I think somewhere over here. Yeah, 40 hertz. I don't know. Yeah, 40 hertz, that's what the output action is, right? And if the output action is running at 40 hertz, but the camera is running at 30 frames per second, I don't know what the policy is. I'm assuming the policy, right, is if they're telling me that what's going here is 40 hertz and what's coming here is 30 times a second, does this get duplicated? Are you sometimes giving it double frames, or is this only running at 30 hertz and you have like a second joint controller that is running at 40 hertz? I don't know. I don't know what exactly that means, but 64 at 40 hertz means that it's looking a little bit over a second back in time, right? Or if it's 30, that means it's kind of looking 2 seconds back. So these robots have like kind of like a short-term memory of 2 seconds. Question from Boo, but why is it looking back? I think looking at possible future states is more important to playing football. You're right in the sense that you're describing, Boo, what is called as planning, right? So in planning, you're thinking about what you're going to do in the future, right? And usually that's done with some kind of MCTS, like a Monte Carlo tree search, where you're looking at possible futures and kind of exploring those possible futures and then using that to determine what you're going to do. But that type of MCTS stuff is very memory and compute heavy, right? Because you're kind of creating this tree of possible futures. You're not going to be able to run any kind of like planning like that on a tiny little edge device running on a robot, right? So that's the reason why they're not doing this kind of like planning, forward-looking stuff. These robots are just barely like they barely know what the fuck is going on. You know, they're just like sitting there and they have access to kind of a little bit of what happened in the past, and then they're just kind of stumbling their way towards the ball and trying to score, right? Like, so this is not like super advanced, but in a robot in your home, which has access to a bigger edge device and is doing stuff a little bit more slowly, yeah, you probably have some amount of planning where you're kind of looking ahead in the future. LSTM versus Transformer. Isn't Transformer a better architecture given we attend to the past frames? Yeah, you could use a Transformer. So there are plenty of robotics papers that use a Transformer. A Transformer is not quite a recurrent architecture like this, but you can use it like a recurrent architecture, right? The Transformer, it's consuming a sequence of things, but it's consuming a sequence of things at the whole, like all at once, right? So it's basically doing this attention computation between the entire sequence and the entire sequence. So much like you can decide how far back in time you're going to look when doing this LSTM, you can also decide, okay, well, I can just feed the past 20 states into my Transformer, and there you go. That's kind of equivalent to LSTM that has 20 previous steps backwards. But a Transformer is going to be much more memory intensive and compute heavy, right? Because a Transformer is quadratic with respect to the input sequence length. So if you're looking 64 states back in time, 64 states back in time in a Transformer is going to be a lot more memory than 64 states back in time with an LSTM. The advantage of an LSTM and these kind of recurrent architectures like a Mamba or an RNN, classic RNN if you want to use that one, is that they're linear with respect to that, right? They only need to pass forward a little hidden state right here, this h of t, which is getting passed forward to the next one, and that hidden state has a fixed length. So no matter how far back you look in time, you can always count for that little hidden state to be the same. And if you're going to be deploying this on an edge device like a robot, a tiny LSTM that is limited and linear with respect to the sequence length, it's going to be faster and more efficient than something like a Transformer. But if you have a bigger robot, you can use a Transformer. You can use, I think, an action chunking Transformer is something I've seen before. But I think in this case, they chose an LSTM because of just the limited compute that they have on this edge device. We're at the Ford T era of AI. Yeah, we're not even at the Ford T era of AI, right? So I would say the Model T. So what Model T? What GodBuddy is referring to there is this Ford Model T, which was one of the first kind of mass production cars. But we're not even there yet, right? Because to me, what defines the Model T was the fact that they were able to manufacture them in mass, right? So previously, every single car before the Model T was crafted by like an expert mechanic, right? So you had basically like a expert mechanic dude who like crafted a car, and that's why cars were really only there for rich people, because you basically, each of them was bespoke. And it was really when Ford came in, right, this guy, and he made this manufacturing line, and he could just crank out these Model Ts, and that made them significantly cheaper. But we're not at that point yet. If you look at all the different humanoid robots that we have, none of them are mass manufactured, right? Even the Tesla Optimus or the Figure robot, like the ones at the very head, they're still much more similar to the early cars where they're like bespoke, right? They're like very bespoke things that are being built in one at a time by a set of very experienced people. We aren't at the point of robotics yet where we have kind of like a Model T, right? Where we have like a factory that's just cranking out humanoids and just pumping them out, right? Like, we're not there yet, but we're very, very close. I think we're literally just a couple years away from mass scale humanoids. Okay. Another thing, here's another question by Mitra, and keep it coming. I like having a ton of questions, guys. I think like whenever you guys interact, it ends up for a much better stream than whenever it's just me just kind of reading this paper. They can use event cameras. That way it'd be much easier to track changes, much less data to process. Yeah, so what Arcagiotti there is talking about is that there's these event cameras. These are slightly different cameras. I think there's, let me see if I can find a nice GIF. Event camera GIF. Yeah, here we go. These are pretty cool. Sometimes you see these at events or at conferences, right? People will have these event cameras, right? And event cameras really only look at the difference between frames, which means they can operate, I think, at a higher frame rate, and that they also take less memory. They're kind of more efficient, right? So you can really only see what's moving. And this is actually a really good idea, because if you actually think about this environment, the only thing you care about is like the robot and the ball. I guess the goal doesn't move, so maybe that is a thing. The goal doesn't move, but like the thing with the event camera is that you're kind of ignoring the stationary part of the environment, right? So whenever you're using event cameras, you're basically saying, I don't give a shit about the background, right? Which works in some situations. In some situations, you do want to care about the background, right? Because if you have a humanoid that's operating in the real world, the background contains a lot of semantic information that is useful to completing the task, right? Like, am I in the kitchen, or am I in the bathroom, or am I staring at a wall, right? There's all this background semantic information that you want to use, which is why and where you would want to use an RGB camera. But in something like this, like Robo Soccer, I do actually agree with you that an event-based camera would be better, because it actually gets rid of the background, right? It gets rid of all this. You don't need that semantic information from the background to really solve this task. You only need the dynamic information, which is the ball and the other robot, the enemy robot. So I actually kind of agree with you there. All right. Let's keep going. We were here. We were talking about this. We talked about the LSTM. All right. Now we're going to talk about Egocentric Vision. Pretty good timing on that event camera. Question from Boo. I'm curious, what would that conv LSTM would work in this scenario instead of using a hybrid? I don't know much about conv LSTM. I'm assuming it's just an LSTM that has some kind of convolutional aspect to it. Maybe it works better, maybe it doesn't. Like, most of the time, like, messing with model architecture like that is not super important, right? So like, don't worry too much about like, okay, should I use a transformer here? Should I use this transformer here? Should I use an LSTM or a conv LSTM? Like, those questions, like, usually it ends up not mattering that much, right? Usually what matters is like the environment, the sensing modalities, like how much data you have. Those are the questions that matter. The specific model architecture you use is not as important. So would conv LSTM work in this scenario? Probably work kind of good, but it's not going to necessarily, there isn't some magic model architecture that's suddenly going to make this work a million times better, right? At the end of the day, it's the data and the task itself that is kind of limiting the performance, not the model architecture, right? The model architecture is not the weakest link in the chain. So if you swap it out with a different model architecture, you're probably going to get about the same results. Okay. We provide the critic with ground truth state information, including the egocentric position and velocity of the ball, the opponent, and the goal, and the visual and proprietary set of information that is provided to the policy. Okay, so they're cheating a little bit, but they justify their cheating. Okay, so if you remember, I was talking about how the impressive thing about this paper is that they don't use explicit state information, right? They're not using the position of every single robot, the position of the ball, the position of the opponent, the position of the goal. They're not using that, but they're not using that only for the policy, right? But in this type of reinforcement learning system, this actor-critic reinforcement learning system, there's two actual neural networks playing the game here, right? You have a neural network that is the actual policy. This is what's actually going to run on your robot. That policy, that neural network, only has access to the camera. And I guess it has the proprietary set of inputs, as in, like, it knows where its joints are, right? So this is like the 20 joint numbers, and then this is the 40 by 30 camera input. But the critic, which is a second neural network, and this neural network, because this is trained only in simulation, only exists in simulation, right? You're not using this critic at any point when you're actually running these, right? So whenever you're doing this, this is just one policy versus another policy. There's no critic here. The critic is only used in training to basically push gradients into the actor. And the critic here has access to egocentric location, velocity of ball, opponent, and goal, and velocity of walker. So this is an interesting situation where if you're going to be zero shot transferring from sim to real, then you can use explicit state information in sim for the critic, right? Because you're not going to be using the critic in the real world, which means that one of the reasons why you wouldn't want to use explicit state information is because in the real world, you might not have access to that, right? You might not have external tracking systems that give you the position of the ball. So in sim, you do though. In sim, you know exactly where that ball is because you're simulating it. You know the exact position and velocity and acceleration and rotation of that ball. So you can give that to the critic in sim, so the critic knows extra information than the policy, which means that whenever it's pushing gradients into the policy, it has privileged information, right? So it can actually kind of always stay ahead of the actor, which is important in these kind of actor-critic systems, right? Where the balance between the actor and the critic needs to be there in order to train something effectively. Okay, we provide the critic with the ground truth using information available in simulation. Okay. Would love to see you dig into tuning an LLM with these architectures with different test use cases. Yeah, I've thought about doing some programming streams, maybe going back to that. I used to do more programming streams, but nobody watched them. That's the problem. It's like I kind of there's a kind of like an audience capture kind of situation going on where originally I was just kind of like coding and reading papers and then coding and reading papers, and then I would look back and the coding streams, nobody ever watched them, and everybody seemed to care more about the paper streams, right? I don't know if that's like an SEO thing or maybe just reading papers in general is more engaging than coding, but I realized, okay, well, I should just be doing these paper streams. And I actually used to do them during the week, and then I realized, okay, the weekend is actually better. So I've moved and ended up on this kind of paper streams on Saturdays and Sundays because of just the activity that I've seen. So that's kind of where I am. But if you guys wanted like a coding stream on like a Friday, like I thought about doing that, right? Like a Friday afternoon coding stream. Would people watch that? What's the difference between an agent and an expert? There really isn't a difference there. Those are kind of high-level terms that kind of mean the same thing, right? So you could say that a reinforcement learning agent, the policy is a reinforcement learning agent, but you could also call the policy that gets up the expert, right? Like the word expert doesn't mean anything. You can be used to refer to pretty much any of these things, and the word policy or the word agent also doesn't really mean anything specific. It can mean anything like that, right? An agent is just something that takes actions in an environment, right? And an expert is just an agent that is good at some specific thing. In this case, whenever they're saying expert, right, two separate experts, what they're talking about is an expert that gets up from the ground, which is a policy, which is also an agent, and an expert that learns to score, which is also a policy, which is also an agent. So expert and agent don't necessarily have very specific, narrow definitions. They're kind of broad terms. Okay. There's some guy working with LangChain and LangGraph that's getting traction. Dude, LangChain is kind of trash, though. I'm going to be honest with you guys. It's like a bloated package. You need to extend the horn blowing concept. Yeah. For those of you that maybe don't join at the beginning, I blow this like didgeridoo to announce and end the stream, but I've thought about doing that more. You know, there's like Primogen, you know, is someone that I kind of try to model after, and like people like Primogen, they have this like entertainment aspect to them, you know, where they're kind of just like memeing and they're using like weird keyboards and they have like weird hats and shit like that. Like I'm trying to do a little bit of that too, but you know, sometimes I feel like a clown when I'm just like sitting here, like kind of like trying to entertain as opposed to just reading a paper. Okay, let's go back to the rendering. Generating nerfs of various real soccer scenes from 250 photographs. So to generate this nerf that they use to basically create the background of the simulation, they have to photograph the entire setup. And because their setup changes, right, they actually have a bunch of them, right? So they get 4 different nerfs under different lighting conditions and with different arrangements of background objects. And they randomly perturb the brightness, saturation, hue, and contrast of the input. So what they're talking about here is what's called domain randomization. And the problem with any kind of reinforcement learning or any kind of deep neural network is that it's going to try to overfit to anything that you give it, right? So if you train a policy, especially a policy that is using vision, and it's always the same color floor, it's going to be very specific to that colored floor. If you suddenly change the color of this floor and you've only ever trained with this color floor, the policy is going to behave erratically and in an unpredictable way, right? So the way to fix that is to randomize things like the color and the lighting and the objects in the background, randomize those in training so that you're kind of effectively teaching the neural network to not pay attention to those things. You're basically saying, hey, sometimes the floor is green, sometimes it's dark green, sometimes it's light green, sometimes it's pink, right? And in that way, the neural network learns to kind of ignore those things. So domain randomization is this idea that everything that doesn't matter in your environment, randomize it, right? So make it weird, make it random, change it. And this is very important in vision-based reinforcement learning because vision-based reinforcement learning is already pretty hard. You don't want it to be overfitting to your specific table, right? So domain randomization is important, and they're going to be doing that by having a couple different nerfs that they kind of randomly pick every time. Training from vision is considerably more complex, expensive, and time-consuming than from state. Actors must render at each step and are slower to generate data, and each batch of learning data is slower to process, right? And so this is kind of the curse of dimensionality here, where because an image input of even this super downsampled image like 40 by 30, that's still a lot more numbers than something like this, right? Where you basically have 6 numbers for the, in this case it's 2D, but 3 numbers for the XYZ, 4 numbers for the or the quaternion, right? So like state is going to be a lower dimensionality than vision, and that lower dimensionality means that every single part of this, such as when you're rendering, right, you're not going to have to do that. When you're generating data, it's lower dimensional, so it's faster. Each batch of learning data, you're going to be able to use a bigger batch size. You're going to be able to transfer that batch of data even faster, right? So the cursive dimensionality from vision kind of hits you at all points in the training process. So that's why vision is harder. We reuse transition data from previous experiments. And this is where we're going to introduce this part here, right? So this is the method overview. In each experiment, we train the agent with off-policy RL via replay across experiments. Replay across experiments refers to this paper here, which is also a paper from DeepMind from the same person, Dhruva. And in this paper, they want to reuse experience from previous experiments to improve exploration and bootstrap learning. So experience in this case, you can think of it like training data. It's basically just a picture and then what the robot did, a picture and what the robot did, right? So it's like as the robots are training in simulation, they're collecting experience, and that experience is being stored in what is called a replay buffer, usually, right? That replay buffer, you could think of it just like a database of all the experience. And when that experience is collected by the same policy that you're using to push gradients into from that, right? So like as you're training this, if you're training using data that was collected with the same policy, then you're doing what's called on-policy reinforcement learning. But in this case, they want to do off-policy reinforcement learning, which means that the data that you're using to train this policy might not actually have been even collected with the same policy, right? So it's off the current policy, which basically just means like it's not as related as on policy, the data that would come from the actual policy itself, right? And that's usually kind of tricky to do. But in this case, it's a little bit easier because, believe it or not, actually, the fact that you're doing it from vision means that it's easier, right? If you have state-based RL, the distinction between on-policy, off-policy can be quite big. But if you're using vision, the distinction between off-policy and on-policy is a little bit less important, right? Because a picture's a picture's a picture at the end of the day, and these pictures are kind of randomized anyways. So you can actually get a little bit more signal from that. And in this replay across experiments, what they're doing is you can see they're kind of gradually accumulating more and more data. And then the more data you have, right, deep learning systems and deep reinforcement learning is a type of deep learning. scale with data. The more data you have, the better you can cover the state action space, and the better your policy can find the optimal policy, right? The more data you have, the better you're going to perform. So you're going to be collecting a bunch of data in simulation, right? Your Mujoko physics and your nerf scene here. You're going to be shoving that data into this replay, and then you're going to take that replay and shove it into an even larger database called the replay across experiments. And then whenever you're training your policy, you're going to be using the on policy replay, but then you're also going to mix in, just sprinkle in a little bit of this kind of broader off policy data, right? So it's just kind of a way of getting more data to train on than if you were just using this replay right here. Okay. Maybe explaining the rest of what's going on here, right? So you have your replay across experiments. You're combining that data. You're feeding it into the agent here. The agent is effectively the policy. You have your teacher policy, which is, again, this idea of distillation. The distillation is being KL divergence as the metric between the teacher and the current policy that's being used to basically distill the teacher policies into the actual student here that is the one that takes the actions. It's taking the actions in the environment. The environment gives you the state that results after that particular action is taken, right? So the environment acts as the state transition function and then gives you some reward, and that reward is then used to basically train this critic, and then that critic is used to then train the actor or the policy. And that's basically it. And then when you're actually deploying, so this is all in simulation, but when you actually deploy it, you don't need the critic, you don't need this replay, you don't need any of that. You're just taking that policy, it's consuming the state, and then it's outputting some action. And you're just running that in a real-time loop on the robot. All right. Experiments. Okay, so here's a little bit more information on the robot itself. This is called a OP3 humanoid by Robotis, which is a fairly popular, I think it's actually a Korean company. Let me make sure of that. No, it's actually a China. Oh, wait, what? It's a subsidiary of a Beijing company, but it's in South Korea. Okay, so maybe what happened is that Robotis was a South Korean company that got purchased by like a Chinese holding company. I don't actually know. I don't know the history, but that's the company. They're 51 centimeters tall, weigh 3.5 kilograms, and have 20 actuated joints, so they're quite small. They're just like a little half-meter robot. They have a webcam running at 30 FPS, so nothing fancy here, just like a standard USB webcam that runs at a low frame rate, right? This isn't like some super intense setup. 40 hertz joint position control, also relatively small. They put a filter on top of that to smooth the actions, right? Some kind of Kalman filter is usually a common one that is used, but I think this here exponential filter is a little bit more basic than that. You see they're just taking the current action and then adding it, multiplying it by 0.2, and the current action that you output is action applied to the previous one. So you're not directly outputting the action from the neural net every single time. What happens when you do that is the robot gets like very jittery, right? Because the policy might be like, go forward, go backward, go forward, go backward, go forward, go backward, right? Like, and the robot kind of like vibrates. And so that's why they kind of smooth it. And that's how you get, even with the smoothing, you kind of get that weird like herky-jerky motion that you get from these end-to-end reinforcement learning systems. You can always tell when something is end-to-end RL versus when something is using some kind of model-based like control, right? Model-based control is usually very smooth, right? Like the Boston Dynamic robot motion, versus here, you know it's end-to-end just because of just how weird and random it is. That's the tell. Okay. Emergent behaviors. Let's talk about emergent behaviors. Okay. There are behaviors that emerge, such as searching for the ball, scrambling, and blocking a shot. Okay, so what is searching for the ball? Searching for the ball is, you see this robot up here? It's searching, it's moving its little head to try to find the ball. So it's like looking left and right. It's going like this. It's searching for the ball. That is not something that they taught it to do, right? That is not a behavior that was programmed in any way, right? They didn't bootstrap it from some hard-coded behavior, like the get-up behavior is bootstrapped from a hard-coded behavior. And the shooting behavior is coming from this reward shaping, where you probably have some reward shaping where you're saying, hey, the closer your foot is to the ball, we're going to give you some reward. Whenever you score, we're going to give you some reward. Even if it's not close to the goal, we're going to give you some reward. So a bunch of these behaviors, they emerge, but they emerge because you're doing this reward shaping. But the interesting part about this ball searching behavior is that it's emergent without any explicit reward, right? So the robot learned on its own in simulation that if it doesn't know where the ball is, it should move its head, because if it moves its head, it'll maybe be able to see the ball and then go towards the ball. So that's pretty cool, right? Like, emergent behaviors are really, really cool. And especially in like a just end-to-end RL environment like this, having an emergent seeking behavior, pretty badass. Why is it so surprising? It's surprising because you didn't hard code it, right? It's like there's no reward that like explicitly rewards moving your head around, right? You would think that in fact you won't want to move your head around, because if you move your head around, you're going to like kind of blur your vision, and then it's going to be harder to do what you're doing. But the environment itself created enough of a kind of reward signal that you get this emergent behavior of ball searching. That's why it's kind of cool. Okay. Nerf randomization, the emergent behavior. Probes. Okay, so there's going to be a couple probes here. So what a probe is basically you take your neural network, and your neural network is trying to produce some output to do something, right? What a probe is that you take usually the very last layer before your output, and you try to see how good it is at something else, right? So sometimes people do classification probes where they'll take the last layer of a image stack, and they'll say, okay, well, this last encoded representation of the image, how useful is it for classifying something, or how useful is it for predicting the depth image, right? So in this case, what they're going to be probing is the ability or the representation of the encoded features, that the ability to get a position of the ball from that. So is the position of the ball inside the feature vector that comes out of your model, right? So like, is that information in there? That's what you're trying to ask with that probe. You're trying to say, is that information in there? I'm going to put a little extra little head here that tries to predict that. And if it can predict it well, then it means that that information is actually in there. It's not explicitly in there, right? Because it's just some high dimensional feature vector that is very difficult to understand as a human. But this probe allows you to say that the information is in there, even if we don't really know exactly which neuron it's in, right? It's in some kind of combination of all those little neurons. So here you see the predicted position of the ball based on this probe, and you can see that it does actually have an idea of where the ball is. And if the robot is looking at the ball, the accuracy of that is much more narrow. So you can see that whenever the robot is not looking at the ball, it doesn't really know where the ball is, but it knows it's somewhere behind it. Versus here, it's looking at the ball, so it has a very accurate, this is exactly where the ball is. Right? So I think these are kind of cool. Position prediction. After finding the ball, the predictions become more certain and are relatively accurate. Right? So you see that here. At first, it doesn't really know where the ball is. This is what it's seeing. But then, boom, once it sees that little ball, it's like, okay, I know exactly where the ball is. Pretty cool. Tracking dynamic objects in the visual scene emerges naturally. We measure the angular distance, head movement. Here they're basically just showing you that this head tracking emerged naturally. It's not something that they trained by reward shaping or encouraged. It's just literally happened. Blah, blah, blah. Data source analysis. So here they're comparing learning from scratch versus this retrieval, what is it? Replay across experiments, RAE. So both this red line and this light blue line, which is using that large off-policy database of experience, right? And then kind of mixing that in with your current replay buffer in order to increase the amount of data and increase the variance of your data. Of course, this is a deep learning system, so it makes a ton of sense that the accumulated reward, which is how much reward an agent is able to get in an environment, which is effectively a proxy for how good that agent is. So you can see that as you're training more. So total online steps, right? This is how steps you're taking in this environment. So the agents or policies that have been trained with this additional off-policy data coming through this replay. I keep forgetting it. Replay across experiments. They're able to accumulate more reward, which effectively means that they're able to better solve the problem of robotic humanoid soccer. For the state-based agent, so they do have both the vision-only agent and the state-based agent. The state-based agent has sources of noise that are difficult to simulate, such as sensor noise, battery state, and the state of the robot hardware. This is why sim-to-real is hard, right? Sim-to-real is hard because your simulation is never really a true representation of your real environment, right? In your simulated environments, the joint encoders aren't the same. The IMU isn't the same. The IMU is different from the explicit state. So there's a big chunk of the state and state space, and even the way that the action gets executed is different in the simulation than in the real world. So that's enough of a difference that transferring a state-based reinforcement learning model is not going to work as well. And that's usually why we had this whole sim-to-real problem, is because we were doing state-based RL. But vision-based RL, especially if you're using kind of aggressive domain randomization like they were using here, that's going to transfer a little bit better. So you sidestep a couple issues by doing vision-based RL, even though it's quite harder than state-based RL. Evidence that argues in favor of training end-to-end from vision over distilling knowledge from state-based agents, such as requiring actively controlling and coordinating movements between the head and the body. Since state-based agents do not require such behaviors, reusing data generated by them may be of limited use and, in the worst case, introduce bias that may hinder learning. So this is another kind of interesting finding in this paper, is that sometimes what people do is they try to distill knowledge from state-based agents. Right? So they're taking an agent which was trained with explicit state information, right? But the problem with that is that that agent is qualitatively different from an agent that had to learn from vision, right? And we were literally just talking about this ball searching behavior, right? If you were trying to distill an agent from a state-based agent, you would never get this ball searching behavior, because the state-based agent knows where the ball is at all points, right? It knows where that ball is because it's getting given that exact ball position. So it never needs to do this little head movement because it knows exactly where the ball is. So the only way that you got this emergent ball searching behavior is because you were training from scratch using vision, as opposed to distilling from state-based agents. So that's just one example of it, but I think that this goes so much deeper than that, right? Because think about every other behavior that this robot is doing, right? Even kicking, right? When the robot kicks the ball, I bet you the vision-based agent kind of looks down at the ball a little bit, right? It's like looking at the ball because it needs to kind of know where the ball is in order to kick it. Versus a state-based agent probably never looks at the ball because it knows exactly where the ball is, right? It knows exactly where all of its joints are, exactly where the ball is, exactly where the goal is. So it can basically kick blind. Right? So I thought that was an interesting thing that has ramifications for just all of robotics in general, right? Where if you're using these explicit states for RL, that can be a bit of a curse because you're forcing your policy to find solutions which might not actually work very well when you're trying to do things from vision as opposed to state. So that was a pretty cool finding. Right? You're introducing this bias that may hinder learning by giving your RL explicit state. You guys would watch a coding stream? I might have to do that then. Shooting after looking. Does Messi look at the ball? I don't think he does, but that's a good point, Spirabell. You're making a good point that an extremely high level agent like Messi is at soccer, he doesn't even look at the ball, right? He has like his ability to like model the position of the ball relative to his foot is so good that he doesn't need to look at the ball at all. But that's like expertise, right? We're talking about like we're just talking about being able to like fucking like just barely get the ball in the goal versus like be an expert. So maybe it loops all the way back around, right? And eventually the agent that ends up solving humanoid robot soccer doesn't actually look at the ball, doesn't need to do this scanning because it already knows where it is. Messi should be studied. Yeah, I think he is studied. Messi, so I might anger some people here a little bit, but people need to understand that Messi is a lab experiment. Let me show you guys. So Messi was born, blah, blah, blah. And let me see if I can find this. Lifelong supporter. Messi joined. Here we go. At the age of 10, he was diagnosed with growth hormone deficiency. As his father's health insurance covered only 2 years, blah, 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 he was blah, blah. And then he ended up going to Barcelona. And Barcelona agreed to pay him or to give him his growth hormone. So human growth hormone is a performance-enhancing drug. This is all the athletes are using this, right? Usually you're microdosing this because if you microdose growth hormone, it's basically impossible to pick up on a steroid test, right? Growth hormone is like one of the most powerful, like, performance-enhancing drugs in sports. And Lionel Messi was literally getting growth hormone at the age of 10. So this guy played since the age of 10. He was sitting there in Barcelona's La Masia like camp playing soccer every single fucking day and getting growth hormone, right? So Lionel Messi's like tendons on his feet, right? The musculature in his ankles and his knees is probably like inhuman, right? Like we're talking about if you give growth hormone to a kid and they play soccer all day, they're going to be really good, right? And somebody who like just played soccer in a favela and never got growth hormone since the age of 10, like they can't even compete with that level of intensity. So yeah, Messi is amazing. He's great. Probably the greatest soccer player of all time, but you gotta, there's a little asterisk there, right? And this is a guy who has been on growth hormone since he was a child. So I don't know. That's the dirty secret to Messi. Okay, I think I pissed off all the. I do think he's good. I think he was definitely head to head with Ronaldo for some time, but then when he won the World Cup and Ronaldo just retired to play in Saudi Arabia, I think at that point he passed Ronaldo a little bit. So I think he actually is the best soccer player of all time, but as I said before, he literally had growth hormone since the age of 10. You know, it's not a fair comparison because most people don't have that. And that's like, in some ways, you could almost think that that's like illegal, right? Like imagine if you were giving your kid growth hormone, like at some point the Child Protective Services would be like, excuse me, you can't just like inject your kid with growth hormone so that they're an athlete. But because he was like quote unquote growth hormone deficient, it was totally okay for the La Masia Barcelona camp to like inject him with growth hormone when he was 10 years old. I don't know. It seems a little sketchy, right? So he's kind of like one of the few people that got away with that. And that kind of PED use like kind of snowballs. And by the time he was like 18, like, you know, I'm sure his tendons are literally like twice as thick as the fucking everybody else's tendons. Ronaldo did not get that hormone. Yeah, maybe he did. I think all of them are on HGH at this point. Pretty much all of them are on testosterone as well. But yeah, I don't know. I've heard the word steroid goblin used to describe Messi, which is particularly heinous. All right. That's pretty much it, guys. What else? Is there anything else here? POMDP. This is the domain randomization that they use for the nerfs that kind of jitter the hue, saturation, brightness. We went over this. Model architecture is very small, little robot. So your models are going to be pretty small, very small little ResNet, very small little LSTM. Everything is pretty small. 64 V100 GPU actors and a TPU V2 learner pod arranged in a 2x2 topology. So, of course, Google DeepMind, they're going to be using TPUs. Batch size of 80, which is small, right? And why is that a small batch size? Because each data point has an image, which is high dimensional, right? So in a state-based reinforcement learning, your state or your input to your neural network is very small, so you can have very big batch sizes. But whenever you're doing image-based RL, you can't fit as many images as you can states, so you're going to use smaller batch sizes. Max replay size, this is the size of the replay buffer, right? So this thing here. How many trajectories are you keeping in that replay buffer before you kind of overwrite them? You have your different learning rates for your actor and your critic. You have your KL divergence. Discount factor, this is how far back you go when you're doing credit assignment. That's pretty much it, guys. To the best of our knowledge, our work is the first demonstration of real-world transfer on vision-based policies trained with end-to-end RL for a dynamic, long horizon task. All right. Let me sip some water. You guys ask some questions, and then we'll summarize this stream. Boo is asking, what is the data size that they used? So I don't know if they give us a number explicitly here, but in a simulation, in a reinforcement learning with simulation case, right, there's two kind of things going on. There's what's called the experience collection, and then there's the actual training. So training, what you're doing is you're taking batches from your replay buffer and your larger replay buffer here, and then pushing gradients into the policy. But then you actually have the experience collection, which is where you're going to take your policy and run it in the environment in order to collect states and rewards, and those are the little tuples that end up in your replay buffer. So you're using your policy to collect data points, and those data points are being mixed in with historical data points to then train your policy, right? So it's kind of like a self-play kind of loop, similar to like the DeepMind Alpha Zero kind of situation, where the games of Go that you're using to train are coming from the policy itself. So it's like generating its own data that it's then using to train, right? So this isn't like a language model that just kind of has some like static training data set, and then you just train on that data set for like however many epochs, right? This is kind of like a self-play loop where it's generating data to then train on, to then generate data to train on, which actually we are seeing in large language models. So even though I brought up large language models as an example against that, they are doing that, right? We saw in the Llama 3 paper how they basically are using the LLM to generate data, which can then be heuristically checked, specifically programming and math data, and then putting that back into the training corpus and then training on that. So there are self-play loops in large language model training, but those self-play loops were kind of pioneered in reinforcement learning. Okay, you guys are still talking about Messi. What problems are solved over previous related research? So there isn't anything on here that's necessarily completely original. You know, I think all of the different things that they did here, you can find earlier papers where they did them as well. But to me, what makes this paper great is that it's combining all of them, right? It's real world, right? You're actually deploying on the real world. You're showing the real thing. It's zero shot sim to real, right? So you're solving that problem. It's a long horizon planning, dynamic, partially observable, multi-agent, right? You're doing on device, right? So you're doing onboard compute. So you're using vision. That's the big one too, right? Vision end to end rather than kind of external state or Oracle state end to end. So it's really the good thing about this paper is just the fact that it's combining all the different hard parts of reinforcement learning and then jamming them into one problem and giving you a pretty good result for all of those problems, right? So this is more kind of like a success story of more like AlphaGo, right? Where it's kind of like, hey, we did this hard thing that solves all these ancillary problems, as opposed to a paper that's kind of like hey, here's one very specific solution to one very specific problem. How's it going, Aries? All right, let's summarize this. I need to head out soon. Okay, today we had a stream called Egocentric Vision RL. Egocentric Vision RL is a stream on this latest DeepMind soccer paper. DeepMind publishes these papers occasionally. They have a team that works on this. It's called Learning Robot Soccer from Egocentric Vision with Deep Reinforcement Learning. And this paper is pretty badass. They basically do end-to-end vision-based RL, which means that the neural network that is actually running on the robot, which is a ResNet with an LSTM, a little MLP head here, this receives only an image, right? So it's basically going from an image to joint positions, which is the action that it's taking, right? In a humanoid robot, the action that you take is basically a position for each of your joints. You're basically saying, this is where I want to put my shoulder, this is where I want to put my leg, this is where I want to put my knee. And most of the time, right, whenever you see papers and all the previous DeepMind robot soccer papers, they're receiving Oracle state information, right? So usually what's happening is that they're inside a field, and the field has all these cameras on the outside that are tracking the position of all the robots, they're tracking the position of the ball, they're tracking the position of the goals. So in all the previous soccer robot papers, the policy or the actor is receiving all that Oracle information. So it knows exactly where the ball is, it knows exactly where the opponent is, it knows exactly where its foot is. And that is a much easier problem to solve than what they do in this paper, which is they do it entirely from vision, which is higher dimensional. It's partially observable, much harder problem. Not only that, but they also do it entirely on board. So they run the final policy on the edge device in the robot, which is impressive, right? Most robots are not running on board, especially if it's a resource-constrained edge device like this little OP3 humanoid, right? Being able to run on that means you have to make your model very, very small. And when you make your model very, very small, it has less capacity, which means it doesn't learn very well, right? So that's impressive. What else? Yeah, this was an interesting thing. So they do this kind of model distillation to combine multiple models and get it to fit on this edge device. So in distillation, you are taking a teacher model and distilling a student model from it. So you can do distillation for the purposes of training a small model, which you will be able to deploy on an embedded device, a small edge device. But in this case, they use distillation for multiple reasons. So they use distillation to combine a get-up policy and a scoring policy, right? So combining two different expert or teacher policies into one much smaller student policy that kind of does both of them and also is small enough to run on device. So I think this is a pattern that we'll see more often in reinforcement learning. And I compared this against the usual pattern that we see, which is kind of like a hierarchy of policies where you have kind of higher level policies that choose lower level policies. But the problem with that is that you can't run that on an edge device because you can't have multiple policies loaded, right? you can usually only barely have one policy loaded. So I like this idea of distilling in order to have one policy that runs on the robot that takes up the full compute budget of the robot, rather than having kind of like an ensemble of different policies, which is really only possible if you're using cloud computing or some kind of externalized computing for the robot. Right? Multiple GPUs, right? If you have like a tractor that has like, it's autonomous, it might have 2 or 3 different GPUs on it, and each GPU is running different parts of it. Okay. They do this fancy stuff with nerfs where they kind of render the background, kind of do a little bit domain randomization there. And then one of the cooler parts of this is that they had emergent behaviors, right? So being able to learn from scratch using vision means that there was specific behaviors that they never really had any reward shaping for, right? So the one that they kind of use as an example is this ball searching, where basically the robot develops this ability to kind of like just scan its environment constantly, looking left to right to left to right to try to find the ball, right? And they make a very good point that that type of emergent ball scanning behavior is not something that you would ever get if you were using state-based agents and you were distilling from that, right? So if you were trying to distill the final policy from a policy that was trained in simulation with explicit state, it probably would not have that scanning behavior because it always knew exactly where the ball was. So I think this is a good kind of warning for people in the reinforcement learning and robotics space that you have to be moving away from this state-based RL, because vision-based RL is really what you're going to end up using. And in vision-based RL, you're going to end up in a different part of action and state space than if you just use state-based RL. So that's pretty much it, guys. Pretty cool little paper. I just love this series of works. You know, like, these robots are just so cute and they're so interesting. And, you know, I really hope that DeepMind continues to fund this research lab, because every time they release a paper, I love seeing it and I love reading it. That's it, guys. Thanks, everybody. Thanks, God Buddy Ed, Boo, Aries, Khalil, Snooks, Rene, Spirabel, Pratyush, 87GN, Arkagiati, Maximum Claude, Beyond, Boo again, Arkagiati again, Zayu Zhang, Siraj, Kelsum Fonyansun. I'm going to get your name right one of these days. James McLean, Khalil, Zenji, Brian, Sarah. Thanks, everybody, for listening. Hope you had a great time. Hope you have a great week, and see you guys later.